will be of interest to you guys that are in the audience. So again, this work again is done mostly by my students. How do I use this? Oh, I just put it. Okay, just with pointer. Okay, gotcha. Right. So this is done all by my grad student Tran Nguyen, who was not able to be here because of some visa issues. So I'm going to do my best to represent her work, basically. So again, this is our first attempt to create glutamate biosensors using essentially direct printing, which is a different technique, hopefully an easier way of fabricating this type of implantable biosensors than conventional MEMS, which we're also doing as well, but we're trying to facilitate the translation and the scalability, and in order to do that, we're trying to make that a little bit faster. So just outline of the topics we're going to go over briefly about some of the work that we're doing, the big picture of our research overview, and the application, which is the spinal cord injury, and then the role of glutamate in terms of excitotoxicity, why we want to create printable biosensors, our design application results, and what we're going to do from now, and then just summarize the whole talk at the end. So this is what basically happened when a bunch of us just kind of get together and just start thinking about solutions to problems that nobody really cares about. So unless we talk to people like Nigel, or in our case, Professor Riyi from vet school, we want to know why we're creating the solutions that they need, because otherwise we're just going to make devices that nobody really cares about. Just the big picture of our lab is to create, to address some of the challenges in medical devices, especially in the realm of implantable devices. So if you plot different types of implantable devices, or medical devices in general, as a function of risk and expected lifetime, and as you go from a more disposable devices to a more subcutaneous devices, something that lasts even longer, like a central line, and to something that you want to have in your body forever, essentially some sort of a neural interface and sensor and things like that, the risk goes up precipitously. But inversely, if you take a look at, if you plot the same kind of thing as a function of reliability, it goes down very, very rapidly. So there's an opportunity here to make some of these interface devices, sensors that you want to have in your body for a long period of time, like Elijah mentioned, the reliability, increasing the reliability is key and critical importance. So just to give you a brief sense of what happened, what's going on with the state of the art in terms of commercially available implantable sensors, Lycox brain tissue oxygenation monitor only lasts about 2 weeks before it gives out erroneous measurement. The doctors cannot rely on this to make any kind of meaningful clinical decision. There's a new development in terms of continuous glucose monitor. Now the state of the art is to be able to replace the sensing components of this every 10 days, which is better than before, but still it's not good enough. And there are some efforts to create these optical sensors that can last longer, but ultimately you want to have this like forever. You want to set it and forget it. So that's kind of where our lab is focusing on, trying to use different types of approaches, both materials as well as the active components, to be able to address some of the issues with the reliability of implantable devices. So just briefly, why the implantable devices have such a poor reliability? There's two major parts. So one is that the body itself does not like things when you try to jab things into it. So it thinks it's something that's harmful to the body. It's try to wall off against it, causes some inflammation. There's a lot of risk for infection and things like that. But there's also concerns of device reliability from mechanical and the functional physical point of view. As an engineer, we can actually deal with this pretty robustly by over-engineering our requirements. However, these biological responses is really difficult to deal with. Even with materials and clever designing, it's hard to kind of suppress the immune system and these kind of things from preventing our devices, allowing our devices to work for a long period of time. So I'll talk about what we are trying to do in the future just in a bit. So again, back to our story for this talk, we're trying to better understand spinal cord injury. This is the work that our collaborator Riyi is doing. He's wanting to understand what happens in a spinal cord injury, more or less. So this is a cartoon view of what normal spinal cord looks like. There's a bunch of neurons that creates exons that travels up and down the spinal cord. When you have a the spinal cord injury, you have a either crushing or some sort of mechanical insult to disrupt this kind of connection that you already formed in the nervous system. But that's bad enough. But what happens is after you have this kind of disruption, it releases a whole bunch of deleterious material like glutamate, other types of oxidative species, and causes inflammation response to kick in. So, but it's really unclear why and the extent and the duration of this kind of electrochemical, the chemically mediated secondary injury processes happen. So he came to us and said we need some better tools to be able to measure this because they were using microdialysis, which has inherent time delay of up to 30 minutes. So we wanted to be able to take a look at some of the other options, and electrochemical sensor is a very good opportunity because it's easy to more or less to fabricate, and obviously people like Hel and Nigel has been using it for a while. So I'm trying to get into this. And why do we care about glutamate? So not only is it used typically for neurotransmitting purposes to cause this kind of excitatory behavior from the neuron, it's also a precursor for GABA. It's a constituent for proteins, and also works in energy metabolism. But we're mostly interested in this neurotoxic effect, because what happens when you have abundance of neurotransmitter in the extracellular space, it starts to overexcite the neurons surrounding it. And when there's overstimulation, these neurons actually die, which propagates these the secondary injury mechanism. And we wanted to better characterize that in terms of better spatial and temporal resolution. So this is our approach to create this more or less simple devices to facilitate testing of these type of devices in vivo. Obviously, when you talk about using microfabricated devices, it costs a lot of money and effort to actually be able to change the design and to optimize the spacing and create multiple functionalities and things like that. But using a print direct writing technology, we can basically draw any types of sensor in terms of shape and design by controlling the parameters of printing, like the pressure and the speed of extrusion and things like that. So not only can we do this at a macro scale, we can also use pooled micropipette to create really small structures. We can reliably print up to about 30 to 40 micron line width, which is sufficient enough to create microscale implantable biosensing elements. Not only that, we can also use it to directly do the drop casting so that we can have a better control of where the enzyme gets located, which allows us to have eventually multifunctional capabilities by putting a different enzyme on this. So briefly, the fabrication method is much simpler than conventional MEMS. We start with a glass slide with PDMS layer, which is only about 10 to 20 microns thick, which makes it very, very flexible. And we basically just kind of draw our electrode on it and create the contact pad using silver paste, and then use a laser cutter to just kind of outline this, and then functionalize it with the enzyme and just lift it off. That's ready to be used then. We can also use other rapid prototyping technology like a maskless lithography and also oxygen plasma to create a little bit more stiffer electrodes, because we found 10 to 20 micron thick PDMS is very floppy. We can't cut it in the body, in the spinal cord. So we either need to do some stiffening or some other coatings to be able to allow us to implant. So we use a little bit stiffer material, LCP, which kind of demonstrates this functionality to be able to print it on any kind of substrate, planar as well as non-planar substrate. And that's kind of where it's important, because I'll talk about that in the future works section. So I'm going to skip this because Nigel already talked about this. Essentially, it changes the glutamate into hydrogen peroxide, which can be oxidized to create this kind of signal when you apply glutamate in it. We use Amperometric, just like Nigel mentioned. And just to be able to kind of compare a two standard way of glutamate, we use MEMS fabricated microelectrodes as a control. To see how their performance change. This is basically cannibalizing on other projects, microelectrode arrays, and just functionalized it using the same method, and then just created a MEMS fabricated glutamate biosensor. Just to compare, this top section is from MEMS fabricated devices. This is the Amperometric response and the calibration curve to hydrogen peroxide as well as glutamate. And then this is the result from the direct writing. And the sensitivity is pretty close. It's not as good as the pure evaporated platinum, but what we use is a PDOT, which is conductive polymer, mixed with the carbon paste that are activated, as well as microparticle. This is just a commercially available material we can just buy and just put it right directly into our dispenser and just kind of start printing. So it makes it a lot easier and cheaper as well. But in terms of sensitivity, it's pretty similar. And the level of detection, limit of detection is pretty good, less than 1 micromolar. But the problem is the response time is a little bit larger in scale than the platinum, as Nigel mentioned. But this is a function of the enzyme and the types of materials that we can potentially tune. So, and the fact that we don't need to measure a rapid, immediate response, although we do see some pretty transient graph in our preliminary ex vivo in bioregulations. So again, selectivity and dynamic range is very important. We use Nafion as well. It's pretty good against ascorbic acid, uric acid. We don't really worry about dopamine because it's spinal cord, but it's pretty responsive to the acetaminophen, which is abundant in Crab solution that we use in perfused samples of the spinal cord. So this is potentially a confounding problem. We're trying to reduce that as well, but the signal to glutamate is pretty robust. So hopefully that the signal to noise ratio is going to be enough for us to get meaningful results. We do have some preliminary data to show that. The Riyi range is from 1 to 800 micromolar, which is sufficient enough for our application because in spinal cord, the extracellular concentration of glutamate is about less than 20 micromolar. And in an injurious model, it goes up to about 600 micromolar. So this is sufficient in terms of the need, the engineering challenge. Stability of the device is very important. We did a preliminary study just by storing the device in PBS for low temperature for 6 weeks and just retested it. There is some degradation before and afterwards, about 80%. This is pretty much in line with what we expect based on literature value. But obviously, we want to repeat this test in a more physiologically relevant testing environment, like in a body temperature PBS or even in a in vivo model. So just briefly, this is the preliminary ex vivo evaluation where we use the LCP-based glutamate biosensor and use micromanipulator to actually penetrate into the spinal cord and begin reading essentially what's happening with the glutamate level. This is just raw data of one of our first experiments. Continuously monitoring. This is when you start calibrating in the Crab solution outside of the spinal cord. This is what happens when you insert it. You have a huge amount of glutamate being released because of the injury of physically putting the device in there. After time it stabilizes, we actually remove the device just to see what happens, and then we crush the spinal cord from outside using our crushinator. I forget the name that they call the little machine to crush the spinal cord. But once you do that from outside, while the electrode is measuring glutamate concentration from outside, you can pick up this signal from the sensor. And if you insert the device again, you see again another spike for the glutamate being released. And while it's inside, now we crush the device, the spinal cord again, and you see a huge peak in glutamate concentration. Remove it, reinsert it again, and then we crush the spinal cord again just to measure what happens to it. So essentially, this is kind of a proof of principle demonstration of that it can actually measure glutamate concentration in the spinal cord. What we want to do, just like Nigel mentioned, we want to be able to kind of understand dynamic process of spinal cord injury from a glutamate concentration perspective as a function of space and as well as time. So you want to put the device in there and injure the animal and see what happens to the glutamate level away from the injury site over a period of time, which we think is going to result in some interesting results. So what's next? So we mentioned kind of why we want to use these printing technology for doing this type of thing. On the other half of our lab, we're creating these anti-biofouling devices using mechanical actuation, magnetic power. So what we want to do is we want to combine the actuation and the sensing capabilities together so we can actively combat some of these biofouling that occurs that limits the reliability issues of these implantable devices. We're also working with our collaborator that has the capability to do this wireless telemetry and recording, and then package it all together to create this kind of perpetually functional, hopefully implantable biosensor that can last more than 90 days in the body. So just briefly to summarize, the take-home message I want you guys to take is to the reliability of implantable devices is a very important problem that needs to be addressed. And the glutamate is a neurotransmitter that has multiple roles, especially in spinal cord injury and other kind of neurodegenerative disorder that has the problem with excitotoxicity. And the researchers and engineers need to work together to come up with better tools to kind of understand this kind of basic questions. And direct writing glutamate sensor is good enough from our preliminary results. Hopefully, we'll get additional information. And then the combination of top-down microfabrication as well as bottom-up directly printing the devices can lead to novel multifunctional devices. So this is our acknowledgement of our funding sources and the collaborators and the people who actually worked on this project. I did have a picture of our lab, but it's gone now. But I have the acknowledgement, so thank you.